Okay, I think it's time to get going. Welcome everyone. Good afternoon, good morning, good evening, wherever you may be, and thanks for joining us at DVCon 2022. My name is Matt Graham, and I am a product engineering director here at Cadence, responsible for a number of things like vManager and some other tools that you're going to see today that are sort of regression level verification tools. Joining me today from Cadence will be John Rose, who's one of our senior product engineers in the Xcelium space, and Daniel Hansson, who is formerly the CEO and founder of Verifighter and more recently a member of the technical staff here at Cadence, again in the sort of regression management and auto debug area. The way that our session will work today is John, Daniel, and I have pre-recorded a brief presentation. I say brief, about 45-ish minutes, maybe a little bit longer. And then we have a live demo, and then we'll have the Q&A session at the end. And I believe the way that the Q&A session will work is that if you have questions during the session, please feel free to put them in the chat box, and we'll do our best to answer those kind of verbally at the end of the session. And of course, feel free to reach out if you have any questions at the end of this. Reach out to us or reach out to your local Cadence representative. They'll very much know how to get in touch with each of us. I don't believe we have any other housekeeping or anything like that. I think I guess one thing, as you have probably all read in the way in, is everyone will be muted and your video will be off during the presentation. I will be muted, my video will be off as well, and you'll be seeing the recorded session. And then, like I said, Daniel actually will be doing the demo at the end of the video, and you'll be able to see his screen and be a little more interactive at that time. So unless anything else, I don't know if there's anything from the DVCon folks that I forgot.
No, I think we're all set. We can start the pre-recorded video. Thank you.
All right. Thanks, everybody.
Hello, everybody. My name is Matt Graham, and I'm a member of the vManager product engineering team at Cadence. And I'll be speaking along with my colleagues, Daniel Hansson and John Rose, in our workshop today entitled Machine Learning Driven Verification, a Step Function in Productivity and Throughput. The agenda for today's workshop is, as you see here. First, we'll start with some look at what is machine learning, and then how can it be applied to formal simulation and regression testing as part of a verification effort. Then John will talk about improved bug hunting efficiency with machine learning. Daniel will talk about leveraging machine learning for automatic debug of regression failures. Then we'll have a summary and wrap up and some quick Q&A. So first off, what is machine learning? How can we define it? And how can it shorten the verification cycle? There's been a lot of sort of confusion. I wouldn't say confusion necessarily, maybe, but certainly cross usage of terminology between artificial intelligence and machine learning over the past several years, as both of these things have become prevalent, and the terms are sometimes used interchangeably. So I wanted to take a few minutes and just sort of define them, at least as we see them. So first, if we look at artificial intelligence, often, when somebody's speaking of artificial intelligence, you'll see some sort of brainy electronic crossover pictures like you've got here. But if we look at the sort of formal definition, it's really sort of, intelligence that are demonstrated by machines as opposed to natural intelligence displayed by animals, including humans. So, some sort of intelligence, some sort of the ability to make decisions or achieve some sort of task by machines instead of humans. If we sort of refine that a little further and talk about what's an algorithm, I think an algorithm is, as you see here, we've got some examples of flowcharts describing an algorithm. On the left is Euclid's algorithm for finding the greatest common divisor of two numbers. And on the right is actually an algorithm for pacemaker therapy in a pacemaker type device. This is kind of an open source diagram, but it's basically in both of these cases and many, many others, it's a finite sequence of sort of well-defined instructions. typically used to solve some class of specific problems or to perform a computation. And I got that definition off of Webster's dictionary or something similar. And in this case, we're not, we are doing something intelligent, right? But we're just making a set of predefined, pre-coded or hard-coded comparisons to make decisions, right? Every time through this algorithm, we're going to take the same set of inputs, compare them in the same way, and come up with some sort of operations or set of decisions. If we compare that to machine learning is more the study of computer algorithms that improve themselves automatically. So whereas on the previous slide, we saw algorithms that are sort of fixed in nature, machine learning is these evolving algorithms that use experience and data to be able to sort of improve themselves over time. And it's seen as a part of artificial intelligence, but a sort of specific application of specific structures, such as artificial neural networks, decision trees, support vector machines, and genetic algorithms. Again, effectively, the idea is that we're learning as things go on. So it's not just an algorithm that's applied over and over again, but rather, and each time that algorithm is applied and a certain set of inputs and outputs are considered, the algorithm has the ability to sort of observe what happened, compare it versus goodness or badness, and then improve itself over time. And I wanted to illustrate that through a comparison to a feature we have in vManager called test weight optimization. And then, answer the question, is this machine learning or is it simply automation? And again, we often overload the description of these of similar solutions by saying anything that's algorithmic is machine learning. Somebody make the joke, if the if statement was invented today instead of 40 years ago, we'd call the if statement artificial intelligence or machine learning, and that's not necessarily the case. So let's take a look at our example. The test weight optimization feature in vManager basically takes a set of tests that we're going to run as part of a regression. Let's say we've got 3 different tests. It runs each of those tests some number of times and then adjusts the weighting of each one of those tests. So let's say in the first iteration, we ran each test 25 times. We looked at the output and then we adjusted the number of tests that we are going to run in the second iteration based on the output of the first iteration. But that's based on a goal setting, and it's a specific algorithm. It's not really doing learning. It's not improving the algorithm each time. It is automated, it is algorithmic, but it doesn't learn. If you were to put the same data through again, it would give you the same output sort of over and over and over again, because again, it's not learning, it's not improving the algorithm, it's just applying the algorithm and applying some automation. It's applying it iteratively, but it's not improving the algorithm, it's not changing the algorithm based on the output or the goals. So again, it is automated, it is algorithmic, but it's not necessarily learning. So with that kind of understanding of the difference and the categorization of machine learning versus algorithmic, how can we apply these to formal simulation and regression testing in the verification domain? How can we apply sort of this self-improving, truly learning algorithms? And obviously, to be able to figure out how we want to apply these, we need a goal. And the goal, of course, is to address the challenge on the left-hand side here. And we won't talk about, our reference to Moore's law or the fact that verification is getting harder and bigger and the state space is growing and so on. I think that's all kind of generally accepted. And so what we want to adopt is kind of this return on investment mindset of not only improving the raw algorithms themselves and the speed at which they run, but also improving overall the kind of bug finding and closure per dollar invested per day of engineering time spent. And effectively, that's improving verification throughput overall. We want to get to the end as quickly and efficiently as possible, however we're defining the end, coverage, bug rate, total time spent, whatever it is. We want to make sure that we get the sort of the most ROI for the effort, energy, and dollars invested. So to that end, we can look at applying machine learning in a number of different areas. We can look at things like coverage regain, so the ability to shorten the amount of time it takes to get to a known good point. we could look at failure triage, so the ability to look at failing tests or failing messages and sort of bucketize them or triage them automatically. We could look at, optimal engine selection, so applying machine learning to figure out, what is the best way to attack a given problem. And then the two that we're going to talk more about today, which is bug hunting. So, how can we apply machine learning to go get into the areas of the design where bugs may reside or may still be hidden, and bug prediction. So before we even run simulation, how can we, or given a set of simulation results from the past, how can we predict which bugs may exist in our code? Because of course, in reality, bugs are just something that exists in the code as a result of our development process. So if we can find them even without simulating, or find them with more effectiveness without having to simulate or run formal or whatever, so much the better. So with that introduction out of the way, I'll turn it over to John to talk about improved bug hunting through machine learning.
Okay, thank you, Matt. As Matt said, my name is John Rose. I'm the product engineer for the Xcelium machine learning tool. And so today, I want to talk about a specific aspect of Xcelium machine learning. But first, to get started, I want to talk about what Xcelium machine learning is for those who may not be aware. So what Xcelium machine learning is it's a tool that trains network on a large set of regression runs. So you train train this model in order to create this correlation between some input variables, tests and random variables, toward an output goal, in this case, coverage, right? So, conceptually, it looks like this. You have a bunch of random controls that build all of these models, and you have a coverage focus that you're going toward, right? And the end goal of Xcelium ML is to make your regression more efficient. So you started with this training data, you have thousands of runs, and what you want to do is get those thousands of runs down to hundreds of runs, and do it in a way that still replicates the intent of the regression. So for example, we have these charts here that show the hit rate of coverage bends, right? And in the original regression, you have a chart that looks like this, where you have a bunch of coverage bends that are hit rarely, a bunch more that are hit a lot, and then a lot that are kind of in between. And the goal of Xcelium ML is to magnify how well those bends get hit, to push these guys at the bottom up. So the bends that are hit by 0.5% of runs get hit by 2% of runs, or some such thing. And it's trying to magnify the rate at which coverage gets hit to replicate what you're trying to achieve in your regression, but do it more efficiently, right? So that's the goal. And this chart is another view of the same above, where this is showing a histogram of this magnification of coverage bends. So you'll have some bends that only get magnified a little bit. Maybe the hit rate goes up 5% or 10% because they were already hit, say, near 100% of runs. And you'll have other bends way out here, these outlier bends that get magnified by 10x because they were sitting down here at the bottom. And now, instead of only being hit by 1 out of 1,000 runs, they get hit by 10 out of 1,000 runs or some such thing. But in general, for this technology, you're going to be living in this space where the hit rate of bends is going to be magnified in the 2 to 3 X kind of range. And again, the whole point here is efficiency, making the generated regression more efficient for you. So that's great. You've got these more efficient regression. So what can you do with that? So the obvious thing you can do with that is just have more runs of a similar regression over time, right? So you may replace the original regression with a generated regression, and you run more simulations over a certain period of time. Okay, that's fine. The other thing you can do is target specific areas of the design to focus runs on some particular part of your design that you want to magnify. You want to have this kind of magnified effort on, and this is kind of an augmentation. So you have your original regression or a subset of your original regression, and then you've got some augmented runs to help put stress on some area of the design. And then for the purposes of this talk, the focus is more on how this technology, or how the effect of this technology can be used for bug hunting and coverage closure. These are kind of related, they're different, obviously, disciplines, but they're related to each other, and the same things apply here. So in the bug hunting realm, what we're talking about here is, the nature of Xcelium ML is to magnify coverage points that are already hit. So if you have a case where you have certain coverage that is hit rarely, maybe in this case 5% of the time, so you have this kind of case, and you need certain conditions to occur to expose a bug or hit a hole, then what Xcelium ML is doing for you is increasing the probability that you're going to get to that condition. That's the nature of how Xcelium ML works, and so that's what you're getting out of it. Right? Okay, so sorry about that, I went too far. So what do we do with bug hunting? So how does this apply specifically to bug hunting? So typically in the verification effort, we get to a point, so obviously throughout the effort we're trying to find bugs, that's the point of it, but we get to a point in the effort where the bug rate starts going down in some way, and we want to somehow stress the environment to try to find bugs. So this is what metric-driven verification is all about. We have all of these random tests. These random tests have some random input state that generate random data, random sequences throughout the test that eventually lead to random or different design states that happen. And we suspect that there's some latent bug signature living there, and we're trying to find it. That's what we're trying to do as verification engineers. And so the question is how do we expose this latent bug? How does it come out? So the way we typically do that is we say, okay, give us more resources. Let's just keep running our random simulations and see if we hit some bug signature. And if you have sufficient resources and you've got sufficient interesting upfront scenarios, maybe you'll hit these bug signatures. So in this little diagram, what it's trying to show is you run many random scenarios, and you come close to hitting a bug signature. You don't know this, but you've created some rare cases that have come close to hitting a bug signature, but you didn't. And so eventually you go on and you say, okay, well, I guess I'm happy, I'm done. So the question is how can Xcelium ML help based on the way it behaves, based on what it's trying to do? And as I mentioned before, the point of Xcelium ML is to magnify how we hit coverage. And the result of that is that the ML generated regressions are going to have a tendency to create more of the maybe rarer input states, I guess I would say. So it's going to help focus on these input states that have, again, are hitting more of the coverage area. But what the net effect is for you as the engineer is you generate this set of runs using Xcelium ML, similar to the way you were doing things before, but now the environment is constrained somehow so that you're getting more random sequences in, say, the rarer areas, and fewer random sequences that are easy, that are normal, that you're hitting all the time. So now you're running these sequences, you get close maybe a few times, and now you have a higher probability of exposing this bug that previously was not exposed by you. Or maybe it would have been exposed by you if you had run just more iterations, but you decided to tape out before it was exposed, right? So that's the general idea. So, what does this mean? Again, this is just the way we normally do work. We have our typical project timeline. We're finding from the start of the project to the end of the project, we're finding certain unique bugs per simulation hour or CPU hour that we run simulations on, right? And the typical exposure rate will have a graph something like this. I mean, it's obviously going to be different for every situation, but it'll be something like this, where it starts at some level, goes up to some peak bug rate, bugs are fixed, things are changed, the design stabilizes, and then over time it becomes just a verification effort to hit harder and harder bugs. Eventually the bug rate gets low enough that you say, okay, it's time to tape out, right? This is our normal way of doing things. And that would be using the standard regression as it is. With Xcelium ML, you can add a set of regressions. You could look at the Xcelium ML regressions. Let's say you trained on data here. Xcelium ML may produce a small number of unique bugs if you're comparing unique bugs with respect to what was generated by the original regression. Over time, the number of unique bugs you see from the Xcelium ML runs is going to increase. It's because the full regression is requiring more runs to expose bugs. The ML regression is seeing those bugs sooner, so you're getting day to day more bugs from the ML regression. And then again, over time, the ML regression is going to stabilize too, but as you get later in the project, the expectation is that more of your unique bugs would be coming from this ML generated regression. That's how this would work. So you can obviously look at the cumulative rate. If you were to do this from the start of your verification cycle to the end, you would end up with a cumulative bug rate. You may choose to not start the machine learning aspect until your bug rate in your full environment is dropped down to some threshold so that you can consume this, however you choose to do it. But either way, what you're doing is augmenting what you would otherwise get. So you end up with some kind of a Venn diagram, of bugs that are found in the full regression, bugs that are found uniquely in the ML regression, and then you have obviously overlap between them. So this is kind of how this would work. So that's all I have to say on this today. So I am now going to hand over to Daniel to talk about more things you can do with machine learning and verification.
Thanks, John. I'm Daniel Hansson, the founder of Verifighter, the company behind pinned down the automatic debug tool, which is now part of Cadence. And I'm basically continuing the same kind of work there with automatic debug and ML-based bug prediction. And I'll show you what that is. All right. All right. Okay, so in a standard regression flow, which is the upper half of the slide here, everything is basically automated except the debug of the failure. You have teams committing changes during the day. You run regression nights overnight or several times per day, and those are normally kicked off automatically on a cron job at certain times. But that automatically launched test suites are then manually debugged, and then those bugs are fixed. So the last missing piece of the automatic regression flow is to automate also the debug process. And that's what Pinnan is trying to do, remove the last human in this process here, who looks very sad, by the way, here also. And the result of this, we've measured at customers that it saves both time and effort as the bug churning goes faster. And we measured in one project that it saved up to 5 man years and 10-11% shorter project time. Now, sorry. Okay, so now what's unique with Pindown is 3 things. The end result is a bug report, which is, here's an example. So that consists of matching the test failure with a code change in the revision control system. So the bug report contains the test, the C, the build, the error message. That comes from the customer's test system. And the lower part is, this guy Praveen, he did this change in Perforce or Git or Subversion, and Pindown mapped them together. So the number one thing that Pindown does, which is unique, is that it uses machine learning based bug prediction to guess before simulation starts what change has caused this failure. And the second one is what we call validation, which is even more important, that it proves that that change actually did cause the bug by undoing just that change, rerunning the test, and make sure that pass again before you send out the bug report. So that means quality bug reports. And the last thing which is unique with Pindown is that it doesn't just stop at the commit level. You can tell it to go further inside a commit and point out a single line, even though the commit may have been consisting of updating 1,000 files or something like that. All right, so if we start with the bug prediction, how does that work? So first of all, we have implemented more than 100 features which are generated mostly by looking at the code or the revision control system. So Pindown interfaces directly to the revision control system and sucks out the code and the revision statistics from Git, Perforce, etc., and creates features which are then fed into the machine learning training, so that these different features are weighted together, and some are excluded and some are selected. And the end result of that process is a bug prediction model. Out of more than 100 features, typically only 20 survive, the 20 best ones. And those are balanced by this machine learning process into one unified predictor. And that predictor will be generate a value between 0 and 1, depending if a commit is considered risky, which is 1, or not risky at all, which is 0. So every commit in the range. So say if you have had 100 commits since yesterday's run, Pindown would classify all those 100 commits and then sort them in risk order in order to see which commit is the highest risk. So that bug prediction model is used before simulation starts at time 0. But then we still do the same process of doing this code repair, which is basically just backing out the bad code and validating that that makes the failing test pass again before the bug is reported. So the end customer doesn't see any difference in the bug report, except that it comes earlier. So it's we use ML here basically for efficiency. And I think in general, that's where ML fits very well, to use in a contained environment to make something more efficient. Now, so far, it may have sounded a little bit fluffy, but just to give you some concrete examples on some of these 100 plus features we have, I'll show you one example, which is commit time. So it's a really simple feature, which is the local time when the committer committed the change. And there are a lot of research done that shows that the peak risk of a commit is 3-4 p.m. local time, because at that time the engineers want to go home. They may or may not be ready, but they definitely want to go home. So they have like a hidden agenda, so that they may not actually be that ready. Whereas if they commit something at 11 p.m., it just means that they're ready. So there is an added risk just by looking at the time. And there's also an added risk at looking at the end of week. So at the end of week, you want to kick off a big regression run running over the weekend, whatever the state. So people tend to push in junk at the end of the week. And I know one company, they even forbid end of the week check-ins. You had to do it the day before the end of the week in order to give them at least one day to fix simple issues. So commit time is one good feature, even though it's simple. Another one is file ownership. If you look in the revision history of a single file, and you see that every single commit is done by the same user, then it's low risk. This person knows what he's doing, so there's little risk for misunderstanding, etc. But on the other hand, if there's a file where lots of people are committing, it's high risk, especially if a lot of people are committing at this very moment, the last 2 months. If that's where the major development is going on, that's very high risk. So both of these two features are, they are weak predictors on their own. They mean nothing, but they tend to give some weak prediction of what is a good and bad commit, and together with many other features of similar nature, they can provide a good joint bug predictor. So the end result of this is that we have achieved 41% precision for this bug prediction model, which means that if Pindan says this bug, this commit is a bug, there's a 41% chance that it is a bug also. 41% doesn't sound much, maybe, but it's at 0 time, so it's pretty quick. And if you measure how often people make mistakes when they commit to revision control systems, roughly 4%, maybe 4 or 5% of commits are bad. So it would be a 4% precision of just making a wild guess without ML. So 41% precision is 10x improvement. And every time you guess, you get like a 41% chance of picking the bug. So if you pick the top 6 commits, there's a 96% chance that the bad bug actually is in the top 6 commits. So if you imagine you have 100 commits, you can first focus on the top 6 risky commits, which is a much smaller task. And in 96% of the time, you will find the bug there. So it's very good for performance. Another way of measuring how well it works is this measurement we did at the customer. So this may sound, I had to give some background so you can understand this graph, but basically we looked at 53 validated bugs at an AC customer summer 2020. So after the fact, Pindan knew exactly what commits were bad. And after the fact, we looked at, okay, what did the bug prediction say? What ranking did the bug prediction say? If the bug prediction works, they should have been ranked as the highest risk, because in the end, when they were validated, they turned out to be the bug. And so how often do you get to rank number one? And if you look at this graph, rank number one, the ideal is the most common ranking, which is good. But on top of that, 51% of validated bugs have ranking 1, 2, or 3. And that's a magic number, because Pindan allocates 3 slots in the beginning of a run. Before it has started to do any search or anything like that, in parallel to that, I should say, it guesses with 3 slots where the bug is. And this means that in 51% of the cases, in half the cases, it guessed correctly. And that meant that Pindan came back with the answer within one single iteration. So you can imagine you have a test that takes 1 hour to run. You have 100 commits. In order to convert the failure to a pass, you have to run it at least once with some things backed out. And in 51% of cases, it just took 1 hour to get that bug report, which is pretty good. So yeah, so basically it works even at a customer. Now, the final thing I should say before handing back over to Matt again is that now that we're part of Cadence, we can integrate and play around with a lot of tools. So we have a much bigger playground now. And one of the things we have already done now is that if customers have vManager, we have tightly integrated Pindan with the vManager over its REST API called the V API. So if normally you have to tell Pindan how to rerun tests and how to extract test results, that's part of the Pindan setup. But you don't need to do that for vManager. You can, if you put vManager and Pindan together now, Pindan will know how to rerun and how to extract results without human intervention. So it simplifies how we do the setup. And in the future, we haven't been with Cadence for a long time, but in the future, we also plan to look at all these fantastic data now, which is available with all these different Cadence tools, and feed that into the bug prediction model and improve it further. It's going to be an interesting field to see how that goes. All right, I think it's back over to you, Matt.
Yep, thanks, Daniel. So we wanted to look a little more at, what are we specifically doing at Cadence in terms of applying ML across our various tools. And we spoke obviously today about Pindan, a new addition to our portfolio with the acquisition of Daniel and his team from Verifighter. John obviously talked about what we're doing with Xcelium, and in the interest of time, we unfortunately don't have time to go into detail about what we're doing in Jasper, although it's been around for a little while, and I think we've seen this at Jug and other events. And that is how we're using machine learning inside Jasper as part of something called Proof Master, which allows Jasper to sort of store proof profiling data based on previous proof results. And then when a given property is rerun, it it basically allows us to look at the most efficient way in which that property could be run and was run, and then understand which kind of engine internally to Jasper is most efficient. Then we can apply under this multi-advisor proof orchestration capability some machine learning, such that any new proofs, especially ones that we find that are particularly similar, can be applied to brand new proofs and improve the overall sort of out of the box experience within Jasper. So while not only can we optimize across subsequent runs and regressions, we're also able to farm that information and optimize the sort of new proof efficiency or proof performance kind of out of the box. And in particular, this was something that was highlighted by the nice folks at DeepChip as kind of one of the key differentiators of Jasper. Again, if you're interested in more information about how we're leveraging machine learning inside of Jasper, it's again kind of an out of the box thing, but feel free. There's lots of collateral on cadence.com, and certainly in past jugs, or get in touch with your local Cadence representative. And sort of bringing that all around to a conclusion point, if you like, we can now see where across the full verification flow, or at least a majority of the verification flow. Now, we haven't talked about Palladium and Protium today, and tools like Perspec or System VIP or VIP. But across, the Xcelium, Jasper, vManager, and I'll add Pin down into that vManager category on the regression level, you can see that we're applying machine learning in a number of different ways. In the vManager world, we talked about bug prediction. We're also using machine learning for failure triage. It's a capability that's available in vManager today. Again, if you're interested, feel free to reach out to your local Cadence representatives. In the Xcelium world, John talked about bug hunting with Xcelium ML, and of course, you've probably seen lots of press and lots of use case examples of our coverage regain capability, which again, sort of John sort of high level described in today's presentation. But there's a couple of applications of machine learning within Xcelium there, and then, as I just mentioned, the proof orchestration inside Jasper. So we're really, not looking at machine learning as being one, as applicable in one particular area. It's applicable across multiple areas within the verification flow. So to sort of summarize and wrap up, as we sort of stated, our problem statement or our initial thesis was that improved verification throughput via automation is an absolute necessity. We can't just rely on the simulator getting a little bit faster, CPUs getting a little bit faster, the formal engine getting a little bit faster. We need to start coming up with more novel and more sort of complex and more automated approaches to improving verification throughput. And this provides us with an opportunity to apply machine learning, although, as we saw, not all automation is necessarily machine learning. There is, as both John and Daniel described, a significant potential for machine learning in bug hunting and bug prediction, and these are areas where we think we can have, not just the 5 or 10% improvement that we might have in for example, simulator performance, but where we could end up with a true step function in terms of efficiency and throughput, getting an order of magnitude potentially better in terms of efficiency of finding bugs and identifying bugs and fixing bugs. And so as a result of this, our kind of goal or our vision of having that step function, we're applying machine learning, like I said, across the various pieces of the verification solution. So, finishing up, I'd like to thank everybody for their time today, for joining us in our workshop here. We're going to turn out for a little bit of Q&A now. If we're unable to get to your question during the sort of interactive Q&A session here, feel free to reach out to John, Daniel, or myself. You can see our email addresses here, or again, your local Cadence representative, and they will be more than able to put you in contact with us. So again, thanks for your time. Let's move to the Q&A.
And actually, as I wrote in the chat, the video is not quite correct. We actually have a demo to show before we jump into Q&A. So I'll invite Daniel. I believe you should be able to go ahead and just share your screen and walk us through what you've got to show. You'll have to unmute yourself as well.
All right, hello. I found the mute button. That's always the biggest challenge. The rest of the demo will be easy now that I have found the mute button. So we've seen at the end, or somewhere in the middle when I talked, I'm going to continue from that point. So I mentioned that we have started to integrate pin down with the vManager. And that's what I'm going to show here in this mini demo, and also how it's linked into waveforms and stuff. So feel free to continue asking questions in the chat window, I guess. Now, let's see here. Okay, so vManager. So you don't have to integrate pin down with vManager, but it works with any regression test suite. But if you have vManager, you first run a regression test suite with the vManager. So in this example, there has been 27 tests run to test this little UR demo. 12 of them passed and 15 failed. Now, in this demo, vManager then kicks off pin down to debug these 15 failures, and there's only one bug here. So pin down will select the fastest test and debug that to find where this started to break. So goodbye vManager view for a while, and let's bring up the pin down debug log. So this one shows what steps pin down did in order to take the failure, which failed on the latest, and produce the bug report. And I can go straight to the end just to show here at the end. This is the bug report, which we will get to soon. But basically, this commit is bad. It was validated true because pin down managed to back out a failing commit, a bad commit, and make it pass again. But how did it get to this point? All right, so if you look in this section here, it says debug iteration 1. All of these tests are done in parallel, and there were only 7 tests run here. And actually, it was the same test. This one test was run on different versions of the revision control system. First, it ran it on 4 different revisions. So it ran this test on the latest revision, and it stepped back in time on a slightly older one, and an even older one, and then eventually on the oldest one, it found that the test used to pass on this old revision. So now Pinna knows that the problem is here, and this example is super small, so I can capture it all on the screen. And but so you can see here that this numbering here, which is per force numbering, by the way, it says 52 here, and then it started to fail here. So 53 is the failure. So we have found the tipping point here. Now, but that's not the end of it. So the end of it is the validation, which I said in my presentation. But all this is happening in parallel, all these things. So you can see that in parallel here, Pinnan tried to validate, which is to back out just this bad commit. And as this was done in parallel, Pinnan didn't know which one that was actually bad. So he was just doing it speculatively. But the one that passed was the last one. And you can see that it makes sense because in the last one, it backed out 30753. And 30753, you can see here, it happens to also be in this small example, the first one that failed. So in just one iteration, this small example, Pinnan has gone back and found the pass-fail transition, and also in parallel is managed to speculatively validate it. And once that is done, it sends out the bug report. I'm just reading the questions here. No, I see from Tom here that the added RTL bug commit message. This is a demo, so we have introduced the bug here, but yeah, it's not always that customers are so nice, so they actually say when they created the bug report. But okay, so next step here is that, so if we just summarize where we are, we had the V manager running this small test suite, pinned down, found and validated which was the bad commit. And now we have these changes listed here, which was done in this bad commit. For example, you see RF data in was changed here, and some adjacent signals. Now, what Pinnan did in this setup also was to prepare the waveforms for both the failing and the passing scenario. So that's the next thing I want to show you. So you see here it says passing waveforms, and down here it says failing waveforms. So this was run in the same run. So when the engineer gets the bug report, this is all the waveforms are there available to read. And as I showed you here in the bug report, you have it was RF data in was one of the signals that was used here or changed in this commit. So that's why we selected to trace RF data in. And as you can see here on exactly this time point, there is a difference in the waveform here. In the passing one, on exactly this time snapshot here at 16 nanoseconds, 16335 to be exact, there's a signal change, but in the failing one, there's no signal change. So from this point, Pinnan has shown you exactly where to start looking, and then from here on, you'll have to do manually try to fix this. I see some incoming question. Okay, so the question I got here from Unat is, what happens if the test bench test settings have changed in between those pass-fail seals? How will it correlate the test? Does it do some additional checks and stimulus? All right, so there's one important thing here which I haven't mentioned, and that is that Pinnan considers everything in the test bench and everything in the RTL, as long as the person who set it up have told Pinnan to track both the test bench and RTL. And in that case, if there's a dependency between test and RTL that are so tightly correlated that they need to be considered, then Pinnan may end up backing out both. So it may end up saying in the bug report here, it may not be a single commit, but it may be a double commit. It may say that for this specific RTL commit, you need to also back out the corresponding test commit, because only when you back those two out together, the test passes. So any type of dependency between different RTL codes or tests and RTL is tracked by Pinnan by the fact that it doesn't send out the bug report until it really has made the failing test pass again. no matter if it's one commit that has been unrolled or two commits, and they don't have to be adjacent. It could be one commit done 10 commits ago together with one commit that was done 30 commits ago, but when they two are unrolled together, it passes.
I would say, Daniel, maybe we can add to that the pin down and the ML bug prediction that we're highlighting here is sort of language agnostic, right? It doesn't matter whether it's design or test bench, Verilog, VHDL, if you have C++ code, whatever.
Exactly.
So long as that is within the revision control system, and there is a tipping point within your commit tree at which this passed and now it fails. And if there's some commit, again, it can be, as Daniel just mentioned, they can be multiply connected. It could be 2, 3, 4 commits that are all interrelated, having to do with, there was design behavior change and test beds change to accommodate that, et cetera. That can all be highlighted. Now, another thing that's important to point out, right, is that there are cases where a test has never failed, right? A test has stumbled onto a new seed, for example, that is exposing some new behavior and would never have passed at any point in history. Pin down will highlight that to you as well. Obviously, it can't show you a tipping point because no tipping point exists. And to your question, I think about the additional checks on stimulus. This is an area of research, right, where we can start to look into deeper than potentially within EDA, right? We can start to look deeper than just I shouldn't say than just, but deeper than the things we do now, and maybe leverage other data, like combine what's in the waveform with where we know a tipping point may or may not be, and so on and so forth. But
yeah,
sort of outside the scope of what we have to talk about today, I think.
Yeah, no, that's right. So from pin down's point of view, there is everything is files under revision control. Everything is text files under revision control. So it's just a combination. So it is language agnostic, as you said, and it's just a combination of which combination of revisions will make this one or two or more commits pass again. Or as I mentioned in the video, that you can also just narrow it down to, in the same way you may sometimes need more commits to make it pass again. Sometimes you can focus and go down all the way to one single line within a large commit. But again, it's always based on validation, getting back to a passing state. And as you said, Matt, this is regression testing, regression debug. So it has to, at some point, this test has to pass at some point. But we don't have to be aware of that when we start. You can have like 20 failures, and then one spin and kicks off and starts debugging. You can find out that these 20 failures are due to two different reasons. One bucket of failures is due to a specific commit that caused them to fail, but we don't have to know that there is a pass. Pinan will find that out. As you see here, when Pinan explores back in history, it will find out what used to pass and not, and report accordingly. Now, having said all that, the bug prediction mechanism, which was described in the video, is language aware in a different way. So that it's aware of languages in order to predict where bugs are. For example, it's very much more likely that a bug is in Verilog code than in a PowerPoint update, for example. So the bug prediction mechanism is aware of, I think it can detect 400 different languages just to be able to classify them according to risk. But that bug prediction mechanism still has to go through this validation flow. So if you predict whatever prediction that bug prediction makes, Pinan will still do this validation process on and make the failing test pass again before it sends it out So it still has to go to the validation process. But if the bug prediction is good, it may not have to do this binary search in the beginning here, and that's how you save time. All right, I can actually show you in this. This is again a super small example. So I can just show you what the bug predictions look like. And normally you don't just have 3 commits as in the example I'm pointing to now, but it can give you some idea of what the result of the bug prediction is. And it's basically before you start debugging, actually before you even start to run the test suite, you know, the very first thing that happens in regression if you run, say, nightly regressions, is that you check out the latest from the revision control system, be it Git, Perforce, Subversion. Then you kick off a test suite. There's failures, and then you start debugging them. But even before you kick off the regression test suite, Pindown will go in and look at the revisions, look at the recent commits, and classify them according to risk. And that's where it's using this machine learning stuff. Again, this is from my internal test bench, is one of the tests here. And the outcome of this is just that in this window, there were only 3 commits. And they are classified if with a number between 0 and 1. So 1 means certainty, you know, a 1 means a bug. This commit is definitely a bug if it's 1. 0 means it's definitely not a bug. And then you have this range in between. So if you have 100 commits here, then when Pindown starts to debug it, it will start with the most likely candidates first. So it will start from the top of this list. But actually, any human being could go into the system and look at this classification and just see what is Pindown considered to be the highest risk. So even if you want to do manual debug, you can have a sneak peek at this list. But remember that risk is not certainty, so you can't get you can't send bug reports to people just because they made a high risk commit. You still have to validate it either through Pindown's mechanism or manually. Anything else, Matt, on this topic you want to jump in and say?
No, I think it was excellent demo. Thanks, Daniel. I think we probably do want to maybe go back and spend a few minutes on the questions that were in the chat previously. There was some discussion back and forth between Paul and John and Daniel regarding you know, Jenkins and continuous integration and smoke tests and check-in flow and so on and so forth. One thing I will say is that, you know, I don't think tools like Pindown or any of the ML type capabilities that we're considering are replacement for one good methodology, and I think continuous integration and tools like Jenkins, you know, constitutes good regression level methodology. Daniel, by the way, you're still sharing in case you wanted to show us anything else.
Yeah, I want to show something else, but I'm just
oh, okay.
picking it.
And then the second thing I would say about that is that we see, you know, tools like Jenkins and vManager and Pindown sort of playing harmoniously together, right? They're complementary to each other. You know, vManager's regression management tool, Pindown is a debug automation tool, and Jenkins, of course, a continuous integration. And each one of those should and can integrate together. And in fact, we have customers that are using sort of all 3 together now, or well, we have customers that are using 2 of the 3 at least. I don't know if we have one that's using all 3 together at the same time. But certainly in those cases, right, you would expect a higher quality when using a continuous integration flow. You would expect a higher quality or less likely to have sort of, you know, truly brain dead bugs in your main, you know, like a nightly or a weekly regression. But I think as the discussion went along in the chat was, you still are going to have those bugs that are that are sort of deeper into randomization or deeper in the tool as well. But I mean, that's the reason that these nightly or weekly larger regressions exist, and those tend to be problematic. And in fact, for a tool like Pindown, those are where or even application of Xcelium ML for hunting those bugs, those are the kind of bugs that actually show the greatest return on investment, because they would have otherwise consumed a great deal of manual engineering time to go figure out where they were, whereas spending some of the machine time that is if not free, that is, the machines were idle, or is certainly lower cost than engineering time, and can be leveraged again to sort of help alleviate that and speed things up.
I totally agree.
Go ahead.
Here's the slide I just wanted to show also and discuss around. It's actually from DVCon 2019. I'm not allowed. I don't know if you were even allowed to show that 3 years after, but it just shows it on the real data. Even though this picture is not from real data, but these numbers are from real data. So the idea there that when you list these bug predictions in order of likelihood of containing a bug for a large system, then the problem becomes much smaller. So it doesn't affect the outcome. The bug reports are still validated, but getting there is much faster if you can focus on 5-10 of the high risk commits instead of all 100 commits. So in this case we got a 41% precision on real customer data, and that means that when Pindown is predicting, it's when it says that this commit is bad, it's correct in 41% of the cases, which doesn't sound good maybe, but it's 10 times larger than the chance of just guessing wildly right, because in reality, in real life, maybe 1 in 25 commits is incorrect. So if you just do wild guess, it's like 4% chance of finding the right one. But here it's we have 10 times larger chance of pointing out the correct bug and this is just before regression starts. Now this is just for every single bug, but if you then put this ranking together and every time you say this is a bug, you have 41% chance of being correct. After you picked a couple of them, in this example, once you picked 6 commits, your chance of having found the bug is 96% chance that it's in one of these top 6 commits. So basically, you don't have to be right or for every single pick, but you can pick a subset which is much smaller than than all commits, and then focus on those, and then the problem becomes much smaller. So it's all about performance, which I think a lot of machine learning is about performance, getting more juice out. Maybe the same result, but better getting it faster. Right.
So one thing just before you, so I saw another question come in from Ravi. Before we answer that, back to Tom's point, I know it was said somewhat tongue in cheek, but the question was about did we use did the tool use additional or added RTL bug commit message to help find the bug? In actual fact, the commit message is one of the, I think, what do we have, Daniel, 120 some odd different pieces of data that we can and do consider in determining the likelihood of a bug, including potentially what's in the commit message. So there's a broad spectrum. It's not just, oh, let's analyze the RTL and see if we can see where, massive changes were made. It is actually, there's a lot of, psychology of the developer, I think, included.
Yeah. So it's we have more than 100 features which we look at. So and those features mainly try to grab information about statistics on the author, on the group he's working with, the split, the organizational stuff, that kind of stuff, and not so much the core pin down features are not based on the analyzing the code, but that's where we of course have some work. Now that we're part of Cadence, we can get we can expand with tools that do understand the code, and that is going to be an interesting development. But just to let's take Ravi's question before Bill, because I think
exactly.
John needs to answer Bill's question. That's not my table. But hi, Ravi. Good to talk to you again. So Ravi says, how do you decide a commit is bad? I sit on. Is it based on previous regressions? Yeah. So it's basically it's basically if you run with pin down will during months and months of usage at the customer build up a database of what is a good commit and what is a bad commit, and that database is what pin down is using to build better and better prediction models. So when I say a bad commit, I mean that pin down has historically found this bug, and the statistics is based on statistics on the pin down bugs. Now, the next question when I say that, which will come from people, and that's why I said myself first, is does that mean when pin down is installed at the customer that from start you get nothing, because from start there are no pin down bugs, if pin down hasn't run there for some time. But the answer is that pin down will use another type of bugs called mind bugs. So pin down will provide a good bug prediction mechanism already from day one, but it will provide a better one once it's been running for, the longer the better, but after 6 months it will be maybe ramped up to the max. And the mind bugs is a concept actually not invented by us, it's invented by academia, and is basically a way to just read the revision control system, and just by looking at the revision control system, guessing what was a bad commit and a good commit. And that data is, I would say, definitely low quality, but you can instantly get a lot of data. So on average, it actually works. So from day one, we can get 20 to 30% precision, thanks to mind bugs, without having run pin down at all. But then in the months to come, we can increase it to maybe 30-40% precision using pin down. But that's long answer to your question there. Okay, okay, so next question from Ravi is, can this historical based on user, more bugs found in some hierarchy, can this historical based on user, more bugs found in some hierarchy? Yes, if I understand your question correctly, Ravi, our features, what we look for is based on user. What areas does this user, this committer normally work in? Is this area new to the committer, or is it normally in good control of this area? How long has this user worked here? Is this user committing at the end of a day, Friday just before the weekend, or so we do a lot of statistics on the user and what their and their statistics, but it's not a type of statistics which shames anyone. It's just converted to a number, and no names are mentioned. But that's what. And it's not only users, but it's also statistics on the files themselves. Are we now committing to a centrally located piece of the design, or is it the peripheral part of the design? There are ways to find out how architecturally important certain files are in the design without knowing the architecture. these are the kind of statistical metrics which the bug prediction is based on. Maybe it's time for John to, or you, Matt, to answer Bill's question.
Yeah, I'll answer that.
Okay.
Thanks, Bill, for the question. So Bill's question, he kind of had two questions, and so I'll try to reiterate them a little bit and then explain what the recommendation is. So one is, is the recommendation to have ML on constantly training on, well, first your initial training set, and then you run ML augmented regressions. Are you constantly doing iterative learning on that in order to continuously make the regression better? So that's one question. And then the second question related to that is when you're doing bug hunting or trying to get coverage holes or however you're using Xcelium ML, is it better to combine the full regression as you've defined it with the Xcelium ML regression, or just take this augmented Xcelium ML regression and use it? So those are kind of the questions that Bill had. And okay, I'm going to start with the second one first. Is it better to replace Xcelium ML or augment your regression? And for the bug hunting case, it's probably better to use the Xcelium ML regression as an augmentation. So you're going to continue to run your full regression in some way. Now, you don't necessarily have the resource budget to run your full regression and the ML regression, so there may have to be some trade-off there. So you may, for instance, have some tests that you're running with 50 seeds or 100 seeds, and you may choose to prune that down. And Xcelium ML does provide some analytics that would help you understand which tests it thinks are important. Now, again, you have to remember, Xcelium ML, it has coverage as its goal. It sees low hit coverage bands or medium hit coverage bands or whatever. It's trying to magnify those. You're going to end up with runs that are going to stress particular areas of the design, but you may well have tests that you don't have any really good specific coverage for. And so Xcelium ML may say, oh yeah, I may want a run of that test for some coverage bands that are living in the design, but there may not be enough interesting bands to represent how useful those tests are for potentially finding bugs. So you don't want to get rid of those tests. They have some additional purpose that isn't well enough handled by the coverage model. So when you're looking at how am I going to find bugs, using the augmentation, I think, is the right route. When you're talking about, am I going to constantly be relearning, and I start with a training set, and how often do I want to retrain the data? And that depends a little bit on what your end goal is. You can take the route where you train every time you run a regression. You run an ML regression or a full regression, and you take that data and you feed it back into the model to make the model better. Obviously, with any machine learning, more data gives you a better model at the end, and is going to help the ML engine then generate better sets of runs for whatever your end goal is. But for the bug piece of it, you don't necessarily have to do that, right? It's really about, okay, you've created a set of runs that it's still random because that's what your input was, some random thing. It's just has some directed randomness that's going to have or create more scenarios that, as I said, are likely to be a little bit rarer. And just running that ML regression many times, just like running your full regression many times, is going to have a reasonable chance of exposing bugs. If you then take many runs and do the relearning, what you're going to be doing is helping the ML engine understand how those harder to hit bends can be hit more efficiently. So you're going to, even do that better. When you're using Xcelium ML to try to hit coverage holes, it's much more important to do this iterative learning, because in that case, you really need to emphasize specific bends related to some coverage hole to make sure most of your runs are targeted there. With bug hunting, you don't know where the bug exists. So the issue is more about, how many runs can you have that are going to be likely to be doing interesting scenarios that may expose a bug. I hope that answered the question.
All right.
The next question is for me as well, it looks like. And the question is, what are the knobs? So what does Xcelium ML control? So what Xcelium ML does, so one of the controls is the test, right? So you're running a test with n seeds, 50 seeds, for example. The test is a knob. That's kind of the simple knob that would be used by, for instance, vManager for ranking. And then the next knobs, or the next set of knobs, the input pieces, are random variables. For Xcelium ML, it primarily focuses on random variables that are randomized one time in a simulation, or a small number of times in a simulation. The idea being that these random variables tend to be more configuration oriented, or more oriented to the specific behavior that the test is going to take for that run. So you have a test, and if you run it with hundreds of seeds, it's going to have different behaviors for each seed. And Xcelium ML is trying to figure out the high level behavior of the test, but it isn't controlling individual data items that may be, or transactions that may be happening in the simulation. So the knobs are those kinds of things. And yes, they're rand variables, and it is applying constraints. So you can think of it as a DV engineer, you can think of it as if you were to go to some randomized call in your code, and you were to add a specific inline constraint to that randomized call for different runs of a particular test, right? If you were to do that, if you were to say, okay, I'm running test 1, and I'm going to have a big case statement that says, okay, one time I want to add this constraint on top of this randomized call, another time I want to add this other constraint, and so forth. That's effectively what Xcelium ML is doing. It's looking at this randomized call. It's figuring out for a given test how many runs it wants to execute of that test with different kind of biasing on variables. And the answer is no, you don't have to do any instrumentation to your test bench for Xcelium ML. This is all coming from outside, where you'll be provided what amounts to a constraint file from the outside that Xcelium ML, well, the Xcelium will then be instructed to apply to that run. And the instruction tells Xcelium, when you have a randomized call of this specific class at this specific location, or this, this area of the test bench, this is the way I want you to bias that particular call.
All right, so John and Bill, thanks.
Okay.
Now there were some things I want to cover also, and I mentioned that some of the features can understand the architecture and do predictions on that. And that sounded a bit BS. So I want to show that it's not. No, there's actually some truth behind it. So if I share my screen, that's the green button. So what I was referring to when I said this was what was this aspect called? You can see my screen, right? Yeah, you can. Okay, good. Yeah, so this is what I was referring to is something called change coupling, because you can see relationships in the revision control system that you cannot see anywhere else. So in this example, there's one Verilog USB RTL file, and there's one piece of test code written in C, and they are related together. So there's no way a tool can follow through Verilog and follow it to the C code and and trace it back and forth. But in the revision control system, you can see that they tend to be committed together. Not always do they have to be committed exactly together, but close together. So you can see there's a coupling, and this is called change coupling. It's a terminology again invented by academia doing research on this topic. So the change coupling allows you to see connections between different files and modules independent of language. And if you then want to see what modules are centrally located, or more specifically, what files are centrally located in the architecture, then you use something called sum of coupling, which basically it says which modules have most change couplings together with not just one file but many other files, that they sit like the central hub with the sort of spokes out to all the other files that it has change coupling with, and those ones which have this feature which we call sum of coupling, they are centrally located in the architecture. It could be top level wrapper files that put everything together, or it could be like core pipeline steps in the processor, or something like that. So even though Pindown doesn't understand each customer's different design, Pindown has no idea what you're actually trying to develop. It can see the architectural important files through this feature called sum of coupling. So that was one thing I wanted to show. The other thing I wanted to show is I also wanted to show to dig a little bit deeper down into the dependencies. How does Pindown? There was a question before about dependencies between test and RTL, and all that. And I wanted to give you a slightly less fluffy answer, a more hands-on answer on how does that mechanism work. Okay, so Matt, do you want to say something? Your picture plopped up.
Oh, nope, just turning mute on.
Oh, okay. Oh, so your picture turned up when you turn mute on. That's a very that's a feature in Zoom. Now let's see here. All right, so now I want to show you how dependencies are handled by Pindown. Dependencies has nothing to do with this ML bug prediction, but it has everything to do with this validation mechanism, which in the end ensures that the bug reports are good. So I'll just talk you through this example, and you will see how it goes. And feel free to ask questions in the chat window. Now, so let's start with just the simple example here. You have you have a test failing, So these are just revision numbers. This is commits done by different people. And the last commit here, there's a failure. That's why it's red. And previously it's gray because we have never run any tests on those, because there's been multiple commits since last night's run. And this super small example is just one single test. So, oh, am I not sharing? Oh, that's so good. I am. Yes, Alan. All right. Okay. That's why it was blue. Okay. I had selected the screen, but not pressed share yet. So now you can see what I'm talking about. So again, you heard it through my voice before, but now you can see it's true. There's in step 1, there's a couple of commits here. 4, 5, 6, 7, 8 done by different people. We have no idea about the test results, so that's why they're gray. And the last one, revision 9, is failing. So that's just a starting point. So the first thing that Pindan does, and as you saw in the demo, it does basically all these steps in the slide in parallel. But if you take them step by step, first Pindan tries to run the same test and seed on older revisions. So it's failing, passing. And now at this point, we have found a tipping point, number 6. That revision was the first time something failed. But as you know, now that's not the end of it. Now we will do the validation. So in step 3, we will validate, and as we did in the demo. So that just means we back out revision 6. We leave everything older and younger in there. So 4, 5, 7, 8, 9, they're still there. It's only 6 we backed out. We rerun this same test and see it again, but now it still fails. And the reason is that in this example, whatever was done in 6 has already been fixed in 8. So that was a real problem, but it was a simple mistake that was quickly fixed by the same designer. But, so it failed, so Pindan continues, and then it will back out 7 instead and rerun the validation again, basically rerun the test on this new set of files. And in this case, it passed, but, and now comes the big but for the dependency. What if 7 also failed? It could be that there was a problem in either 6 or 7, and there was a dependency in between 6 and 7 that were so tight so that when you separate them, it doesn't even compile. So what Pindan does then is it will try to back out both 6 and 7 at the same time. And if there was a dependency between 6 and 7, now it will pass when both are backed out, and then the bug reporter will report and say the commit, the bug is in either 6 or 7. So Pindan cannot narrow it down to more tightly than that, but it has still proven that the bug is contained within 6 and 7. So and that is how Pindan handles basically any dependency. It doesn't matter if the dependency between 2 commits is such that they don't compile separately. Like I said in this example, it could be a dependency between the RTL code and the corresponding test, which have to be synchronized. You know, if you change the spec, you have to update both for them to make sense. It could be yeah, it could be any number of things. It could be two RTL files that have strong dependency in between them. They still compile separately, but they don't make sense, and they fail when those changes are. You know, if somebody commits multiple changes, not in the same commit, but multiple related changes across 1, 2, 3 commits, then there will be dependencies on those too. And Pindan doesn't understand anything except, you know, how can I make the failing test pass again? If you look at it from a high level, in step 2, we found that the revision number 5 was passing. So once we didn't know that this was a regression issue when we started. We didn't know that there was a pass, but once we found out that this test actually used to pass, then the problem is contained, and we know that the bug will be within 6, 7, 8, or 9. And from there on, it's a converging problem. We know that 6, 7, 8, 9 contains a bug, and it's just a question of what is the minimum number of commits we have to revert in order for the failing test to pass again. That's the question. And in 90% of the case, I should say, it's a single commit that has caused the failure. In 9% maybe, it's a double commit. You can have triple commits, but it's very, you know, it's much more, it's much rarer. So I would say that you will see on a daily basis, you will see if you have a large test system, you will see single commit bugs on a daily basis. Double commit bugs, you know, when there's a dependency, you will see maybe once per week. Triple commits, you will see once per month. You know, anything can happen, but it's just less and less likely the longer time you go. I mean, less and less likely the more commits that are so tightly intertwined that they can't be separated. Another advantage, which is sort of related to this, but it's the fact that if you again skip the validation process from the start, but if you take a, you know, let's say you have 100 commits, something we haven't mentioned is that Pindan is doing parallel binary search, and that parallel binary search is also weighted using the values from the bug prediction. So it's not equally weighted. We test if it's equally weighted and you have, say, 1,000 commits, then you would, if you have a test 10 jobs in parallel, you would test every 100 commit. But if you weight it according to risk, you will maybe amass a lot of tests around high risk areas and not put them equally spread out. But anyway, if we look at the binary search is very fast and very famous. Everybody knows binary search, I think, in this area. But it has one downside. It's very fast, but it will zoom in this case, on a pass-fail transition. But as we saw in this example, you don't know if that bug that was number 6 here, you don't know if it's still open. So you will, with binary search, if you have 100 commits, 200 commits since last night, you will see that it quickly zooms in on a tipping point, but is it the last relevant tipping point? Because in this case, there is no passes after 6. But in a large test suite, when you maybe only test every 10 commits, say, you may have passes in between, but you don't know about them because you haven't tested them. And it's impossible to test every single commit in a linear way, because if you want to rerun, if you have 100 tests, you want to rerun them, you know, every single commit, you will spend ages doing it. So binary search is all good, it's fast, but you need to validate whether that you found the correct tipping point. So that's another scenario where this validation mechanism is good. And you can't really see it in this example because here we have tested every single commit. There's no holes in between them. but validation is perfect to combine with binary search. You zoom in fast on the issue with binary search, and then you find the tipping point, you try it, you find that it doesn't work, and then you zoom in again on a second tipping point, and you try that one, and that one worked. So that's another use point of validation. So basically, the validation is good for. I mean, validation is the key to ensure good quality bug reports, but it's also the key for performance. It's the reason why we can use bug prediction and binary search, which are both good for performance, but they need to be verified because their accuracy is they can be wrong, they can be right, but they're very fast, but they need an external way of verifying their validity. Right, Matt, where are we now with the time and everything?
We're rapidly approaching when we when we would have been sort of starting to count down the Q&A. We're about 19 or so minutes left, but
okay. I see a question coming in from Bill.
I was going to say, I see Bill has another question, which is great. We can keep going. And I think the only hard stop is kind of five minutes before the top of the hour.
5 minutes before. Okay, good. Okay, so Bill have a question here. Is this question for me or is it for John again? I need to read it first.
Yeah, I think it's for anybody. So.
Oh, anybody, even Matt?
Yeah, even Matt can jump in on this one. Yeah.
But it's too difficult for us to make again.
So.
no, Matt. Oh, Matt, he knows you.
Yeah, apparently. Too well, apparently.
Yeah.
So since it's definitely not me, I'll start by answering. So those, I mean, there is obviously this difficulty, right, in any constrained random test bench where you've got something that just fails. It's typically, some sort of clock synchronization issue or something like that, where it's just, you can catch 90% of the issues at not 10% of the issues. And you always end up with some small failure rate. Sometimes it trends even below, 5 or even 1% of the time, and are going to come back over and over again. One of the things I can say in general is that the goal of our overall, kind of ML direction, and this is one of the reasons why we've invested in things like Xcelium ML and in Verifighter, is to leverage, all of the data that we have collected, right? A tool like vManager has a big database under the hood, and it can tell you that, hey, this test fails, some percentage of the time. And it can be, we want to come up with ways to leverage that data so that we can at very least highlight it, right? And say, hey, this test we know fails in some regular interval. So, maybe we don't need to prioritize it for something like pin down to work on, or, maybe there's something we can do with Xcelium ML to understand the causality between the stimulus and the result that enables us to tweak the constraint or something like that, which is a very long-winded way of saying nothing that's a push button today.
But that's good.
There.
Now I understand why he didn't want to answer, Matt. So, but anyway, yeah, sure. No, but Bill, I think that's a very interesting idea. We have actually in pin down, you can just interrogate our database and print out the tests with statistics on each. How good is each test at finding bugs. We call it listing the tests in bug-centric order. So if you have a test that is very good at finding bugs, it's normally because it's fast and it's early in the test suite, and it finds bugs a lot. In our test suite internally, we have 600 tests per revision control system, and for some reason test 11 in our internal test suite is very good at finding bugs. It's for some reason it's always test 11. Test 11 in our internal test suite will always come up on top if we list them in bug-centric order. Now, this is a new idea, which I haven't thought about before, Bill, but in the same way as you can list how good a bug is at finding bugs, finding regression bugs, you could list them at how good they are at, you know, producing what we call always failing bugs. So I don't, again, the same way as Matt, I don't have a solution for it, but I think it's a very interesting idea these would, of course, when we sort them in bug centric order, these would, of course, come up very, very low on that list. But I think this is a new idea you come over there, Bill, because the reason we have produced that list before is to allow, you know, customers to say, okay, put this test very early in the test suite, so you can stop early if something breaks, because you don't want to wait until the end of the test suite to have the good test run. You want them to run early to find issues earlier to save time. But here you could, in the same way, more proactively push these tests to the end, because you know they will not produce anything good. And also you could flag them and say, you know, these are not normally good ones. But having said all this, the cost, if you run a large test suite for pin down to find out that they are always failing, is normally just 2 slots. So if you run with 10 jobs in parallel and you have 5 bugs to debug, Pinna would dedicate 2 slots for each. You know, it will test the latest and it will test the earliest. So let me show you. Share screen. So if you have a lot of tests, Pinna will, for each, you know, it will bucketize you have hundreds of tests, they are bucketized into different groups. For each group, Pinna will pick the fastest test, and for each fastest test, it will just test 2 slots in large test systems. The latest, which is 9 in this example, and the earliest, which is 4 in this small example. If both come back as failure, Pinna will consider them as always failing and ignore them and just continue. But if 4 comes back as green, as in this case, then it will start to debug them. So the sacrifice for always failing bugs is just 2 slots, and people typically run 10 jobs in parallel. So so the cost for always failing bugs, even if they occur frequently, is not that humongous when you debug with pin down. Right, that was my, I'm not sure my answer was better than yours actually, Matt, so apologies for my being offensive before.
No problem.
All right, okay, right, so I'm trying to find my way back through all the windows here. No, that was not the window.
Yeah, no, it's a valid point at the end here. Bill says, I guess another way to think of these is the usual suspects have seeds that pass and seeds that fail. So maybe we can keep track of those seeds and avoid them, or, you know, it doesn't necessarily mean that there's a bug that needs addressing. And that's another, yeah, certainly, again, leveraging all the data we have, what seeds, what passed and failed. And then, you know, is there commonality, or just make sure we don't repeat the same thing over and over again? That's for sure.
That's right. That's right.
Yeah, I think a lot of times this is a failure triage or a bug signature kind of thing, right? It's like the kind of thing that comes to mind from what Bill is talking about are those test bench states that are going to cause the test bench to do something just wrong, and it's going to generate an error, and someone's going to spend time looking at it and say, oh, not this again, you know, shelve it. And if you can somehow have a signature for that your triage can ignore it, or at least lower the priority of, I think that helps. You know, on the Xcelium ML side, when you're trying to focus regressions around bug signatures, yeah, you would want to filter out failure signatures that have traditionally not been interesting. Now, if it's the case that these random things generate interesting failure signatures, but they're just really hard to debug and find, then that's, I guess, a whole nother question about how you how you decide when to take the time to figure that out and whether or not it really needs to be fixed for tape out or not. That's a question we wouldn't try to answer for you.
Yeah. Another thing I was thinking of, which was not at all this topic, but just the random seeds that passed and failed on the same test is and this is not something we have today, but that's definitely something which is of an interest to me, is to try to capture the differences between the same tests with passing and failing seeds, to see if there is some commonality, so that you can that can help you in the debug process. Currently, everything we talked about so far is what we have today, and that is focused on regression bugs. Finding why things that used to pass is no longer passing, and try to help you debug that. But something close to my heart is also to try to capture why some seeds pass and fail, and try to help also narrow down that aspect. And I just came to think of that because of the last statement there from Bill. All right. Thanks, Bill.
All right. Well, it looks like we're exhausting the questions. I had some good discussion. Thanks very much, everybody. I know the chat isn't always the best way to go back and forth, but I think we had some excellent discussion nonetheless. Thanks, Daniel. Thanks, John. I don't know if we have any wrap up from the DVCon side, but otherwise it looks like that's it.
That'll be all. Thank you so much for your time. Have a good day.
Thanks, everybody. Have a great afternoon.
Thanks, everyone. Bye-bye.